Welcome to this lecture series in complex numbers. In this lecture, we'll be discussing the geometric interpretation of product of two complex numbers. And let us recall a few things that we need. So we have looked at the trigonometric representation of any complex number. So if z is non-zero, then one can find a real number r and a theta such that z is equal to r times cos theta plus I sin theta. Even if z equals 0, then one can find such things. But let me just, to keep things simple, whenever we discuss the trigonometric form, we will assume the number is non-zero, although that's not necessary. Okay, we saw a geometric interpretation of addition of two complex numbers z and w. We saw that if z and w are complex numbers, then you complete this parallelogram, and then the remaining vertex of the parallelogram is z plus w. And then the geometric interpretation of subtraction I wanted to give as an exercise, but let me discuss it here. So suppose z and w are complex numbers. Then we make the following claim. We complete this parallelogram by joining w and z and translating the line segment in this fashion to get a complex number here. And we claim that this pink complex number, call it tau, has the property that, or rather tau we claim is equal to w minus z. So why is that? That's because, well, this is a parallelogram. Therefore, tau plus z is w. And if tau plus z is w, then tau is w minus z. So this is a way to look at the subtraction of two complex numbers in a geometric fashion. And many times we just say that this complex number, we draw an arrow, this complex number is w minus z. And when we say that, what we really mean is that the complex number obtained by translating this kind of directed segment with its tail going to the origin and its head going to wherever that head goes is the complex number w minus z. So if you've seen vectors previously, then this makes a lot of sense. Otherwise, I'm sure it still makes a lot of sense. Rather than every time talking about the translated thing, we can just indicate the translated thing here itself in the figure, and that's very helpful to think. Here are some simple problems for practice. And now let us get started with the material of this lecture. So suppose that is a non-zero complex number. Then an argument of z is a real number theta such that z is mod z times mod z times cos theta plus I sin theta. So it's a very simple definition. Basically, what are the angles that you can use to form the complex number z is basically the idea. And when we say an argument, we mean it is not necessarily unique. And let me characterize exactly what are the angles that work. So the next point is about that. So suppose theta is the angle z makes with the positive direction of the x-axis, denoted in this figure. Then the arguments of z are precisely the angles of this form, theta plus 2n pi, where n is some integer. And the reason is very simple. That is because if z equals mod z cos theta plus I sin theta and also equal to mod z times cos phi plus I sin phi, then it follows that cos theta, since z is a non-zero number, it follows that cos theta is cos phi and sin theta is sin phi, and therefore theta minus phi is 2n pi for some integer n. And that is basically the proof of this claim, that if you have found one argument, theta of course is an argument. If theta is the angle made between z and the positive direction of the x-axis, then theta is clearly an argument of z. And once you have found an argument, every other argument can be found via this formula. So it's a very simple concept. I just want to emphasize that argument of a complex number is not unique by definition. It's a family, it's a whole family, but essentially it is unique. Any two different arguments differ only by an even integer multiple of pi, or an integer multiple of 2 pi. Okay, so the notion of principal argument gets rid of an ambiguity that is inherent in the definition of argument. So again, fix a non-zero complex number, and we define the principal argument of the complex number z as the unique argument which lies in this range. So this is the set of all real numbers between minus pi and pi where this is excluded. So minus pi is not in this set, while pi is in this set. The notation for the principal argument is capital ARG. So this A comes with a capital symbol. This notion will be more clear when we take these examples. So suppose we have this complex number z. Then its principal argument is just this angle. Whatever this angle is, in the picture it looks like 2 pi by 3. So this argument this angle is the argument of z. What about this guy? Let's say z is minus 1. What is the principal argument? It is pi, right? An argument is minus pi, but minus pi is not a principal argument. Principal argument has to lie in this range. Therefore, pi is the principal argument of minus 1, or any complex number lying on this negative x-axis. What about this guy? So it's not this. This is greater than pi, so this is not the principal argument. The principal argument is negative of this angle. So if this angle is phi, then the principal argument is minus phi. So it's a very simple concept, nothing to get confused about. A very simple observation is that if z is non-zero, then z upon mod z has the same principal argument as z. Principal argument is unaltered under scaling by positive reals is all. Okay. Product of two complex numbers. Now this is the most interesting thing about about the whole of complex numbers that we are going to discuss anyway. So suppose z and w are two non-zero complex numbers, then let's say z is r times cos theta plus I sin theta, where r is some positive real. W is s cos phi plus I sin phi, s is some positive real. So theta and phi are arguments of z and w respectively, indicating that in the figure. Alright, so let us compute zw. So zw is rs times cos theta plus I sin theta times cos phi plus I sin phi. This is equal to rs cos theta cos phi minus sin theta sin phi plus I times sin theta cos phi plus cos theta sin phi. And basic trigonometry tells us that this is nothing but cos theta plus phi plus I sin theta plus phi. So magically, the argument of the product is the sum of the arguments that you started with. That's very nice. The magnitude just gets multiplied, obviously, but the arguments get added. So that is a very interesting fact. And if we write z in this notation, we write z as r cis theta. So this can also be written as cis theta, and similarly this can be written as s cis phi. Then we see that basically the observation we made just now is that cis theta times cis phi is cis theta plus phi. That's all. So let's remember this and move on. So this observation can be used to study rotations. So fix a complex number of magnitude 1. Let's say theta is an argument of it. Let's say theta is the angle made by the positive direction of the x-axis. And w is non-zero. Some non-zero complex number. So then what is wz or zw? What is this? This has magnitude same as w, so it is going to lie in this circle somewhere. And its argument is just the argument of w plus the argument of z. The argument of, or an argument of w is this guy. And if you add theta to it, you get this complex number. So basically, we just have to rotate w by the complex number theta. sorry, what am I saying? You just have to rotate w by the angle theta, and you get zw. So complex numbers of unit magnitude can be thought of as rotations of the complex plane. They pick a point in the complex plane and rotate them by the argument that they have. And this is a powerful observation, as we will see subsequently. All right. Inverses, well, by what we just saw, suppose we have a complex number of modulus 1, then of course it can be written in this fashion for some theta. Then z inverse is what? Then z inverse is cos minus theta plus I sine minus theta. The reason is very simple, because this is cis minus theta, and if you multiply cis minus theta with cis theta, you get cis 0. Cis 0 is just 1, and therefore indeed this is the inverse of that guy, because producting this with that guy gives us 1. Geometrically, the inverse of that guy is obtained by just reflecting z by, z about the x-axis, which means that z inverse is nothing but z bar. So we observe that for such a complex number, for a complex number with magnitude 1, z inverse is z bar. And this is nothing new, because we already have seen that z bar is mod z square in complete generality. Therefore, if mod z were equal to 1, if this were equal to 1, then of course z bar would be 1, and it's the same thing. So I'm just repeating something we already know, except that I wanted to see it in the light of what we have learned in this lecture. Division, well, suppose z and w are complex numbers, and let me say that is non-zero, although that's not necessary. Suppose that is r cos theta plus I sine theta, w is s cos phi plus I sine phi, then z by w is r by s cis theta minus phi. Because z is r cis theta, this is s cis phi, and therefore z by w is r upon s cis theta upon cis phi. And we just saw that 1 upon cis phi is cis of minus phi. And that's what gives us that. This is equal to that guy. So division can also be expressed in a very neat way. It's nothing different from multiplication, right? Inverses and division are basically facets of multiplication. Okay, so now let us look at an example. Suppose we have A and C are represented by, so points A and C are represented by these complex numbers. I have drawn them here. And assume A and C, assume AC is the diagonal of a square ABCD. So there is some square ABCD, and AC is the diagonal of that square. We need to find the other two vertices. So we are given the complex representations of the two vertices of a diagonal. We need to find the other two vertices. So let us just remember that if I have a square, I hope I can draw a square. It doesn't look like a square, but anyway. So in a square, what happens is the diagonals bisect at 90 degrees. We have A, we have C. If we know A and C, then we also know the midpoint. So let's say the midpoint is M. And what is the midpoint? The midpoint is 2 plus I plus 4 plus 3I divided by 2, and which is equal to 3 plus 2I, if my calculation is correct. I think it is correct. Okay, so that is M. So we also know the midpoint. And the fact is that this complex number, which is the difference of C and M, if we rotate that by 90 degrees, we get that complex number. But we should understand what that means. So if we rotate this line segment by 90 degrees, then we get that guy. Therefore, what we need to do is we need to add 90 degree rotation of this complex number to the midpoint M, and that will give us that point. So I hope that was clear. And what is this complex number? What is C minus M, so to say? Let me label the diagram. Let us call this Z. Let us call that W. Let us call that maybe mu. So what is W minus mu? W minus mu is 4 plus 3I minus 3 plus 2I. So that is 1 plus I. Right? So 1 plus I denotes this complex number, if you know what I mean. If you look at the recall, I discussed what we mean by that. And now we rotate that by 90 degree. How do you rotate something by 90 degrees? You multiply by cis 90. So cis 90 or cis pi by 2 times w minus mu is nothing but I times w minus mu. So something I should have said earlier, but cis pi by 2 is I. I is the complex number which rotates things by 90 degrees or by pi by 2 radians. Right? 6 pi by 2 is just I. Therefore, this is equal to I times 1 plus I, which is minus 1 plus I. Okay. So what we see is that this complex number, which is, let me call, this is D and this is B. So the complex number D minus M is, so if D is this complex number, M is that complex number, then D minus M is minus 1 plus I, because D minus M is the rotation of C minus M by 90 degrees. So if we know D minus M and we know M, then we can find D. Basically, we just add D minus M with M. Therefore, minus 1 plus I, which is D minus M, plus 3 plus 2I. This is equal to D, which implies 2 plus 3I equals D. Right? So similarly, one can find B, and let me switch on the grid to see what exactly is going on. So if this is 2 plus I, if we plot it correctly, we will find that this is D, and we will find that this guy is B, and that's exactly what you actually do get a square. This thing is actually a square. So it's in fact an axis parallel to square. The sides of the square are parallel to the axes. It's a very simple square. Yeah, so basically the idea in this particular way of finding the two vertices is that if we know that, then we know the rotated thing, and we know how to rotate things. We just multiply by iota. If you want to rotate by 90 degrees, then you just multiply by iota, and you add this particular complex number to M, and that's it. So that's the basic idea. And with that, I want to end this lecture. So as usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.